Hey everybody, how we doing today? All right. Today we're going to talk a little bit about what are called redox reactions. In your reading material and things like that, they're called oxidation reactions. But technically, what we have is what are called reduction oxidation reactions, because anytime you have an oxidation reaction or some material oxidizing, another chemical is reducing. And we'll get into a little more detail on that shortly. But we have to understand that when one material is being created or is gaining electrons, another material is losing electrons. Um, Today I forgot to put the objectives for the lesson in, but our objective is to understand oxidation reduction reactions and to learn a little bit about endothermic and exothermic reactions. We're going to talk a little bit about how energy is moved throughout reactions, as well as how electrons are moved in reactions as well. All right. So starting with oxidation reactions, or the oxidizing side of a redox reaction. The oxidation occurs when an electron is lost. So when atoms lose their electrons, the oxidation state increases in the process. Um, Examples of this are iron rusting is an oxidation reaction. So the picture here on the left, when we look at that, the orange coloring and things like that that we see are because of the or oxidation reduction. Oxygen has been attached to the iron molecules, and instead of being Fe, now it's Fe and O. So we have iron and oxygen combined together. We see the same thing in many metals. Another example is copper oxide. Most people don't realize that the Statue of Liberty is actually copper. It just has been oxidized over the years, so it shows this green metallic tint. I grew up and live in the state of Kansas, and our Capitol dome is copper. My entire life, up until about 10, maybe 15 years ago, the dome on our Capitol building in Kansas was that same kind of marine green color of the Statue of Liberty. Now they've gone in and replaced that, took that copper off, put new copper on, and actually put a sealant on it. So now it is an actual copper dome, and you see the copper coloring instead of that oxidized copper. Another example is combustion reactions. So when we burn things like burn gasoline, burn oil, things like that, electrons transfer release energy as heat and light. So anytime you are burning something, that is a combustion reaction, and that is an oxidation reaction. Basically, we are adding oxygen. To be able to burn something, you have to have oxygen. I don't know how many of you have ever heard of what is called a halon system, but a halon system is a system where they have inert gases, and you see it an awful lot in computer industry, where if a fire gets started, an alarm will go off, and you have about 30. I worked in a place that had this. It was a meat packing plant, but still, they had all their electronic stuff in one area, and the heavy duty thinking part of their business. And if you were in that room and the alarms went off, you had 30 seconds to get out of the room, and then it was going to seal itself off, and it was going to push in what are called inert gases, basically a lot of nitrogen, and push all the oxygen out. By taking all the oxygen out of the room, nothing could continue to burn, and that would stop the fire. Problem is, take all the oxygen out of the room and you're trapped in the room. What happens to you? Not good things. So recognize that in a lot of cases, when we're talking about redox reactions, we're actually talking about adding oxygen to something. Now, it's not always the case, but that's how we recognize it in most cases, with especially living materials and things like that. Now, that's the oxidation side of the reaction. The reduction side of the reaction is where the electrons are gained. So one chemical gives up electrons, another chemical gains electrons. So the oxidation state decreases during this process. Examples of this: metal extraction from ores involves reduction. Iron oxide reduced to pure iron loses the oxygen atom. So you have to remove the oxygen from the iron oxide to just make it iron. Electroplating, metals receive electrons in electroplating. This creates a protective or decorative coats on the objects. Basically, electroplating is you are adding electrons to the metal so that now the metal isn't trying to reach out there and grab electrons, in particular from the air, or the oxygen in the air, I should say, to do that. Does that make any sense to anybody, or am I just confusing you all at this point?
I have a question.
Sure. But
Okay. So the first slide it said electron loss, but the second one said electron gain. What is the difference?
okay. Um, all atoms have electrons in their in the shell of the atom. You've you've had some study on matter, and it talked about the nucleus where the protons and the neutrons are, right?
All right.
And then the electrons are orbiting, and we call it orbiting, but they're really just randomly moving because it isn't in distinct patterns. They are randomly moving around the nucleus. Does that make sense?
Okay. Randomly
Okay.
moving.
Now, the electrons that are on the outer shell of an atom, so the furthest ones away from the nucleus, can be attracted to another atom.
All right. All right.
So in this case, one atom can be losing electrons and the other atom that's next to it is gaining those electrons. And by doing that, we have to remember electrons are negatively charged, right?
Mm-hmm.
So if my left hand is an atom that loses an electron, does it become positively charged or negatively charged?
Positive?
Yeah, because it lost an electron. Now it has more protons than electrons. Does that make sense?
Yeah.
Okay. Now this atom on my right hand gained that electron. So now is it positive or is it negative?
Negative.
Right. So we have a negatively charged atom and a positively charged atom. Guess what? Opposites attract, right?
Yeah.
Boom. That's what holds them together. That makes sense?
Yeah.
So that's how redox reactions work. Is one atom loses an electron or multiple electrons, another atom or atoms gains those electrons, and then they are attracted to each other because opposites attract. So that's basically what we're talking about here. Some of it has to do with sharing electrons, some of it has, and we have to realize when I say gain and lose electrons, there's always the slight attraction. Even though this in my left hand lost the electron and became positively charged, it didn't totally lose that electron. It's still trying to gain that one back because that's what it wants. And we just get a charge, we just get that attraction going. We have atoms that share electrons as well, and they do it the same way. They just don't share them quite as equally. I mean, there's a few atoms that do share very equally, a few compounds that do that, but most have a slight charge one way or the other. The electron's a little more attracted to one side of the atom or to one atom versus the other. When we start dealing with metals, metals tend to want to lose electrons. With that said, that makes them positively charged. And because of that, the metals, if you look at a periodic table, you see a kind of staircase over on the right-hand side. Everything on the right-hand side of that staircase is a non-metal. And that staircase moves further and further to the right as you look at a periodic table. Well, why is that? Well, as you go down the periodic table, you're adding more and more energy levels of electrons. So the electrons are getting further and further away from the nucleus. And I liken that to a shepherd protecting his sheep. If the nucleus is the shepherd and the electrons are the sheep, which sheep is the big bad wolf going to most likely get? The ones on the outside of the flock. So the furthest ones away. And if the bigger the flock gets, the more and more electrons you get, the harder it is for the shepherd, the nucleus, to keep track of them all. And they may jump into another flock because they can get closer to the shepherd that way to feel safe. Hopefully that kind of makes a little bit of sense.
I got it.
I've had some pretty good understanding from students in my past explaining it that way. So that's kind of what's going on there. So some everyday redox reactions in our life. Combustion. I've already kind of talked about that a little bit. Fuel molecules lose their electrons to oxygen in combustion reactions. So they release energy very, very quickly in the form of heat and light. They either get really hot or they glow or both. Decomposition reactions are almost exactly like combustion reactions. The biggest difference between a decomposition reaction and a combustion reaction is the rate at which it happens. A decomposition reaction is doing the same thing. It's losing electrons to oxygen, but in most cases, it's at a much slower rate. So combustion happens very rapidly. Decomposition happens slowly. So even if you think about food, you put food into your body, you oxidize that and break it down and do it very slowly. If you were to burn up the energy in, let's say, a Milky Way candy bar at the rate of a combustion reaction in your body, boom, it'd be gone like that, and you'd have heated up and spontaneously combusted. Decomposition is the same type of thing as combustion, only it's doing it one atom at a time. Instead of burning all the carbon molecules and create carbon dioxide rapidly, it peels one off at a time and does it very slowly so we don't heat up and spontaneously combust. Hopefully that makes sense to everybody. So, and then as it says here, energy transfer, both processes involve oxidation with different reaction rates. Combustion releases energy quickly, decomposition releases it gradually. So all we're doing is releasing energy in both these cases. It's just happening at a very slow rate. So, well, high rate or slow rate. So that's basically the difference. Okay. So some redox reactions in our daily life. We have combustion reactions, which occur in car engines and things like that. Photosynthesis is a redox reaction, and it's actually the opposite of the reaction right below it, respiration. Plants convert carbon dioxide to glucose. So when that is happening, they are actually storing energy in a glucose molecule. In respiration, the exact opposite is happening. Either the plant or an organism that is eating the plant to gain that energy, for example, a human being, respirate. Plants respirate too. And that's the exact opposite of, well, how to put this? The reactions end up being opposites of each other. They don't do it exactly in the same steps reversed, but it's close. So photosynthesis converts carbon dioxide into glucose and oxygen, breaking the carbon and oxygen apart. And then respiration does the exact opposite. It breaks the carbon off of the glucose and adds oxygen to it and oxidizes that carbon to release the energy. So photosynthesis stores the energy, respiration releases the energy. Redox reactions happen in batteries as well. And that's what allows electricity to run through the wires. Is one side of the battery is releasing electrons that are traveling, trying to get to the other side of the battery from the anode to the cathode. And what ends up happening is that that electron runs through something that we end up using that energy for. But it's still a chemical reaction taking place in the battery. If you've ever seen a car battery, you've probably seen, especially an older one, you've probably seen oxidation. It's all that white crud that you see around the pins on the car battery. That makes sense? Have I confused anybody too badly yet? Feel free to go ahead and throw questions out here. I love answering questions. Okay, so with that said, redox reactions kind of break down into what we call endothermic reactions and exothermic reactions. And when we are talking about endothermic and exothermic reactions, what we're talking about are reaction types that are either storing energy or releasing energy. So in the case of endothermic reaction, heat is absorbed or energy is absorbed. Endothermic reactions pull heat from the surroundings and the temperature drops as energy is consumed. Now, with that said, that doesn't necessarily have to be heat. It just has to be energy in general. So notice over here on our energy diagram, we have the reactants down here. And as the reaction takes place, and that's why we have reaction progress, as it moves from left to right, the reaction is taking place. Notice that the potential energy does what? It goes up. So anytime you see the prefix endo, that means something is going in. So in this case, endothermic is telling us that energy is going into the reaction and being stored. Examples of that are like melting ice absorbs heat. Photosynthesis captures light from the sun. So photosynthesis is an endothermic reaction because it is storing energy in the products. So the products have more energy than the reactants in the reaction. Exothermic reactions do the exact opposite. Energy flows to the surroundings, which we see as things heating up. Endothermic reactions usually occur, well, not always, but can occur spontaneously. Endothermic reactions cannot. Endothermic reactions, you have to add energy to the system for the reaction to take place. Exothermic reactions can happen spontaneously, which means once the reaction is started, it's going to lose energy. So the reactants have more energy than the products, and then energy is given off. So combustion is an oxidation process that releases energy to the outside system. Does that make sense to everybody? So our reactants have more energy than our products. All right, so if not, let's compare the two. So an endothermic reaction takes in energy, exothermic gives off energy. Endothermic reactions tend to make things colder. Exothermic reactions tend to warm things up. Endothermic reactions are storing energy. Exothermic reactions are releasing energy. So an example plants making food is storing energy. Burning wood is releasing energy. So energy is lost. And when we say lost, it just means it has gone somewhere else. Okay, now I've got a tough question here. I want everybody to think about this, and I want you to tell me, and don't do this until I tell you to hit the enter button or the send button on the chat. I want you all to tell me whether you think this is an endothermic or an exothermic reaction. Type in your answers. I'll give you about 10 seconds. And then I'm going to ask you to go ahead and then go ahead and hit send. And let's see what we're going to have hopefully a waterfall of people sending in answers. And you can tell me whether you think this is endothermic or exothermic. Go ahead and send in your answers. All right. So I got one exothermic. Anybody else? Come on. I know you're there. You can answer these. And it doesn't matter whether you're right or wrong. This one's a tricky one. And I'll explain why it's tricky in a second. Okay. So we got two exothermics. Anybody else? That's okay. Isaiah, you forgot to send it. I get it. No big deal. All right. Come on, there are 6 more of you out there that could give me an answer. I'm going to tell you right now. Isaiah and Jador are right. They are an exothermic reaction. Now, do one of the two of you want to tell me why you think this is an exothermic reaction? Because you're right. I'm going to see your thought processes. Hopefully it wasn't just a guess.
I just looked at the graph and saw the reactions and how it went down in products. So I kind of thought it was releasing energy.
Perfect. That is exactly what is going on. The reactants had more energy than the products. Now, I'm going to ask a question here, and if you answer this, I'm going to be really impressed with your knowledge today. What is happening here in this hump? Why is there a hump here? What is this hump telling us? First of all, let's simplify the question. Do we have more energy here at the reactants or at the top of the hump?
Um, I'm guessing the top of the hump since an
You,
increase.
yeah. I mean, it says here energy's on this side. This is higher than this. So, yeah, there's more energy here. And then all of a sudden it drops off, right?
Yeah.
All right. So, what, and next step, I'm trying to lead you guys through this piece by piece because this is a little bit deeper thinking, but in a lot of cases, students know the answers if they just know the questions and can simplify the questions down. So, what do you, this we agreed has more energy here at the top than it did here at the bottom. So, where did this energy come from? We had to add it, right?
Hmm.
Okay. So, this addition of energy, and then all of a sudden it starts releasing energy, and the products end up with less energy than the reactants. This from here, this level to up here, this red line or arrow set of arrows represents what we call activation energy. And all activation energy is the energy needed to get something to get the reaction to start going. For example, if we have a small pan of gasoline, is that gasoline going to burn?
That small pan?
Yeah, if it's just sitting there, is it going to burn?
No, it's not gonna burn.
Okay. What has to happen to get it to burn?
Heat it?
light it somehow, right?
Yeah.
We add, yeah, we add energy to it. Strike a match, throw the match in there, and what happens? Woo! And then all that energy is released. Well, we
Activate.
had to put in a little bit of energy from that match. Does that make sense?
Say that
Now,
again?
if we added energy by lighting a match and throwing that lit match into the gasoline, that match had
Um,
energy that was burning at the time, right?
yes.
So that, and granted, this hill is way too big compared to what would actually happen to be just a little bump when with the example I'm using. You'd have a little bump and then a big drop off here. But by adding the match, we've added the energy to get the products to start burning or to get the reaction going. Once the reaction's going, once we get that gasoline burning, what's going to happen? It's going to burn until it runs
Stop.
out, right?
Yeah.
Or until we stop it somehow, smother it and not allow oxygen to get to it. So the activation energy is what's represented by this red line, and that we put in, and then we get more energy out. So yes, this is an exothermic reaction. And this little hump, or in this case, a big hump, shows that we have to add a bunch of energy into it to get a bunch of energy out of it. But notice we ended up with more energy out than we put in. From here to here, we put in energy. But from this green line represents all the energy that we got out. Does that make sense?
Yeah. Isn't it kind of similar to potential energy and kinetic energy? I mean,
A
not the
little,
same.
yeah, yeah. I'm trying to. I can see how you relate it that way, um, because basically we have pot- chemical potential energy in
Hmm.
the reactants, and then we add a little more energy, and then they release a bunch. Now, technically, is that really kinetic energy? No, but it definitely looks like a graph you would see. You As you raise something up, you're storing potential energy, and then as it, for example, going up a hill, then once you start to come down the hill, it's releasing energy and it's kinetic energy. So it is and it isn't. So it's kind of a tricky statement. You're making me have to really think on how to explain that.
Oh,
Yeah.
sorry.
No, you're fine. That means you're thinking, and I like it when students are thinking and asking questions that, I mean, I get it. I understand what's going on here, but you're asking questions that are challenging me to be able to explain it in a good way to you. And that's part of teaching. And that's the part of teaching I really like, is trying to make sure that you understand what's going on. So yeah, ask those questions. That's great. I don't have a problem in the world. And if I don't know, I'll tell you I don't know, because there's a lot of things I don't know. All right. So in the end, what do we get out of this? Well, we have different applications for redox reactions and for basically endothermic, exothermic reactions, because in most cases, reduction oxidation reactions are either storing energy or losing energy. This happens in industrial applications, chemical manufacturing, things like that. It also happens in biological processes, photosynthesis, respiration, those types of things. And in both cases, we're either gaining energy or losing energy while we're changing substances, because that is what chemical reactions are. We have the same number of atoms we had before as we do after. It's just how they are arranged or what they're attached to. Does that make sense?
I got that.
All right. If there does anybody have any questions over this, or have I thoroughly confused you all, or you all have, please tell me one way or the other. If I've confused you, say I'm confused a little bit. If you're not confused and you got it, give me a thumbs up or something in the chat. Because yeah, I, without being able to see your faces and things like that, it's very difficult sometimes for me to understand whether you're getting it or you're not getting it. If I were in a classroom, I could look at your faces and I could go, yeah, that one doesn't get it. That kid doesn't get it. Oh, that one does. And then I know who I need to tailor it to. So it's a little tougher sometimes when I can't see your beautiful faces. But anyway, if you don't have any questions, we'll go ahead and call this a day. Thank you for showing up. I really appreciate your time and love the fact that you guys come asking questions. Feel free to do that at any point in time. If you have questions that relate to homework assignments and things like that, go ahead and ask those as well. All right.
All right.
All right. You all have a wonderful day.
Bye. Have a great day too.